Okay, this is the practice exam 3 solutions. Number 1, we have a CDF. Keep in mind, capital F means CDF, which is different than the PMF we're looking at. However, the P of x equals 1, P of x equals 2, P of x equals 3, these are all coming from the PMF. So how do we get the PMF when we have the CDF, essentially? Well, we need to know what's happening at x equals 1. Well, first of all, we see that there's this piecewise difference. So we're coming in from the left side, and then this is what's happening as we're going out the right side, essentially, of that x equals 1 value. And coming in from the left side, if we're looking at the limit from the left side, as we get closer and closer to 1, this is going to get closer and closer to 1/4. So had there not been a jump, our value of the CDF at x equals 1 would have just been 1/4. But it wasn't. What happened is there was a jump here at x equals 1. Something happened at x equals 1. If we plug in 1 to see what actually happened, 1 minus 1 gives us 0 over 4. So we got to 1/2. So we would have been at 1/4. But this jump happened. If you looked at it on a graph, there would be a discontinuity like this. So right when we get to x equals 1, we would jump up. And how much do we jump up? Well, 1/2 minus 1/4 gives us 1/4. Similarly, at x equals 2, something happens. So if we plug in 2 to this, which would give us the limit as we're coming in from the left side, subtract that from actually plugging 2 into this. Notice this is a constant, so it really doesn't matter which value we have between 2 and 3 here. But still, same principle. We're taking the value of 2 from the right, which is 11/12, and minus the value of 2 from the left, which would be 3/4 to get 1/6. Same thing at 3. Add these up, we get a total of 1/2. So this function is basically going along, steadily increasing. At these 3 points, there's a jump in the probability. In other words, because of these 3 points, that's making up half of the 1 probability we're going to have. Where's the other half? We know that probability has to equal 1, the total probability. Well, that's coming through continuously. So in these chunks, we're slowly increasing our probability between 0 and 3 with 3 major jumps along the way. And we'll talk more about continuous probability in this next chapter. So what's the probability our x would be between these 2 points? Well, because there is no jump at either of these endpoints, we're not really worried whether or not this is less than or equal to. So we can tell the probability of x being within a certain range by taking the CDF of the upper limit and the CDF of the lower limit and subtracting the two. So if we do that, we get 10/12. So a 5 in 6 chance that our x value is going to be between 1/3 and 5/2. Okay, here we have some constant c. We know this little way that the different values or the probabilities of the values of x are related. Notice we only have 3 possible outcomes for x. If we let p sub 0 represent p of x equals 0, that's just shorthand to save us some writing because this is showing up quite a bit. We know that p of x equals 1 is c times p0, and that's just coming from this formula right there. P of x equals 2 equals c times p of x equals 1. Substitute out what we know px equals 1 equals. So in other words, we're placing this into p of x equals 1. We're going to have 2 c's then, or c squared. So we know that the probability of these 3 has to add up to 1. So we're just rewriting these 3 in this format. And again, we know that p of x equals 1 equals this, and we know that p of x equals 2 equals this based on the little substitution we did up here. So if we add these up, we know that 1 equals the sum of these three. If we factor out a p0 from these three terms and divide both sides by the result, divide both sides by the 1 plus c squared, we get the probability that x equals 0 in terms of c. Expected value, we're just taking the different values of x. Notice 0 would cancel out the probability of getting x equals 0, so we don't really even have to write that. But we do have the 1 and the 2 as possible values of x, and this is the probability that x equals 1, the probability that x equals 2. Okay, and here we have where we're just adding across here. Let's see. Okay, then e of x squared. Why are we doing this? Because we're trying to get the variance here. So essentially the same thing. The only thing different is the x values that we're potentially getting. We're going to square each of those. So the 1 squared is not going to change anything, but the 2 squared will. So instead of a 2c squared, we're getting that 4c squared right here. The variance then is just e of x squared minus the mean squared, and we get that. It'd be pretty messy to write out, so we just leave it like that. Okay, 3 teams play a series, first team to win 3 games being declared the winner. So what's the probability that team A wins given that it wins the first game? So if we write this out, we know that the first game goes to A. The next ones we're not quite sure how they'll play out, but we also know that the last one gets A. If we're concerned with A winning the series, A has to win the last game, and it's already given that it wins the first game. The question is, what happens in here? Well, we know that there's one A in there. There has to be, because A has to win 3 games if it wants to win the series. What we don't know is how many B won during that time. It's possible B won as few as 0. It's also possible it won as many as 2. So we build these 3 cases, 0, 1, and 2. There are other ways to approach this. Basically, if you look in the back of the book, it goes through a different explanation, and this will give you the same answer. It's just a different way of looking at it that I think is a bit more intuitive. So what's the chance that we have 0 B's in there? Well, in other words, we just have 1 A, and we don't have any B's. And I'm putting P squared. Why not P? Why do I not only care about this A? Well, this A hasn't happened yet, so I have to take into account the probability of this A happening, even though I know that I'm forcing it to be in the last position. Why don't I take in this A? Well, this one is a given already. So because it's already a given, we don't have to worry that. We're living in a world where A has already won the first game. So instead of saying that A has to win 3, we can really say that A has to win 2 more. And if B doesn't win any, that's just P times P to give you P squared. If B is going to win 1, it could either be before the middle A or after the middle A. There's basically 2 different positions. And in either case, so this is why there's 2. In either case, A still wins 2, which is the P squared. But this case, B also wins 1. So 1 minus P is the probability of B winning. When we have 2B, if you think about it, there's 3 things here. There's 2 B's and 1 A. So let's choose the spot for the A, 3 choose 1, or choose the spots for the B, 3 choose 2. Either will give you 3 as a coefficient. Then you have your 2 wins and your 2 losses all factored in. Add those up, you get the probability that A wins the series, given that it did win the first game. What about the other way around, so that it wins the first game, given that it wins the series? We just set up a Bayes real quick here. Notice that we've already calculated this P of winning, given that it wins the first game. what we do need to add in there is the probability of winning the first game, which is just P. So this is all coming from part A. On the bottom, we have the total probability, so we still have that probability that it wins given that it wins the first game, plus we also take into account the probability that A wins the whole series, given that B wins the first game. So even though B wins the first, A could win the overall series, and we calculate that over here. So how are we getting that? Well, here we just freeze, kind of like we did up here, but now B wins the first one. We still know A has to win the last one if it's going to win the overall, and we know there's 2 more A's in here. There could either be 0 more B's or 1 more B. So in this case, we only have two cases. If B doesn't win any more, it's going to go the B that's already given, then A. The chance of that happening, P cubed. If B does win one, well, there's 3 different spots it could go in, so 3 choose 1. Here's the 1 minus P for the 1 game B1, in addition to the given that was already there. And then again, A has to win 3 there. Okay, so we have people entering a casino at a fairly constant rate. I did a video on this already for the exercise, but let me just comment quickly. So 7 every 10 minutes, we can break that down into any time period we want. If we broke it down into 1 minute, for example, it would be 0.7 of a person every 1 minute. It's okay if it's not an integer. That's not an issue for determining lambda. In part A, it would be nice to do a 3-minute block. So in that case, we'd have 3 times the number of people per minute, which would give us an average of 2.1 people for every 3 minutes. Now we want to know what's the chance that x equals 0 in the next 3 minutes. So we just set up a Poisson with a lambda of 2.1. Again, that lambda is coming from the fact that we have 3 minutes, 7/10 per minute. So we're looking at things in terms of every 3 minutes. In part B, we change that to every 10 minutes. We don't have to, but this is a very convenient way to do it, because then we can just use a single Poisson, with lambda of 7 here. And when I say single Poisson, we do have to evaluate it at x equals 0 and x equals 1, and subtract that from the total probability of 1 to get the probability that it's at least 2 people in the next 10 minutes. Notice that the lambda changed from A to B because we were looking at different time frames. Here it's every 3 minutes, here it's every 10 minutes. Okay, we have a game for $2 per play. Each play is a win of $4. Expected number of games played. So this is just essentially a geometric distribution after we get to past the first 4. So the first 4, it's just operating under a binomial distribution. After game 4, it's a geometric distribution. Both of these are pretty common distributions. The weird thing here is that we're going to keep playing until we lose. So geometric, we keep going until we have a success. So there's a couple different ways to do this. We can look at this losing as our success. In other words, we're switching the P and the Q from the typical geometric distribution. So we have 1 over Q as our expected value after game 4. Now, we're also adding on 4 because no matter what, we're expecting to play the first 4 games. And you might say, well, it says we're going to play the first 5 no matter what. Well, the first 4 are guaranteed. And then starting with the 5th game, yes, we will play it, but the results of the 5th game affect whether we play further. So if we look at a geometric distribution, notice that it can't equal 0. 1 is the smallest it can equal. So starting with game 5 is when we're following that geometric distribution. The extra credit then we will take a look at in class.